Okay. Yeah, it's off. All right. The last week, how was the weekend? Okay. Everybody had a good weekend. It is not hot in Beijing. Yeah. I missed the sun. Okay. Okay. So today is going to be a little bit longer class. I don't think we're going to use all 3 sections. I hope not. But Wednesday will be a little bit shorter class. So I want to talk about a topic that seems to be very interesting to many people right now. But this is not a machine learning class. This is a computer systems class. So we're going to talk today about something you probably have heard a lot of, about how we can very efficiently evaluate. What I mean by evaluate is use or run deep networks. And then I'll come back in the second half. I'm actually going to do this backwards. First half, I'm going to tell you how to run deep networks efficiently, maybe in parallel. And then the second half of the class, I'm actually going to tell you how to train the deep networks in parallel. Now, normally we have to train first to be able to use things. But I'm going to talk about it the other way because I think it's a little bit easier to understand. And I'm going to assume that nobody in this class has any experience at all with deep networks. So I'm hoping that the explanation that I give is actually will be helpful to you if in the future you go take a proper machine learning course. So how many people have taken a proper machine learning course? So you've taken a proper machine learning course. 2. Oh, 3, 4, 5. Okay. So some of this stuff may be way too easy, but I'm going to give you my own explanation of this because I think it'll be a little bit different than how you will learn a machine learning course. Okay. So why have you heard so much about deep networks recently? You've heard a lot about deep networks recently because they are a tool that has been surprisingly effective, surprisingly powerful at solving problems that we previously thought were very hard. Things like understanding speech, things like understanding what is in an image, things like playing games. I was at a conference a year and a half ago about playing chess. May have been 2 years ago. And the experts in the world at playing chess were at this conference. And we were talking about why computers got so good at chess. And at that conference, there were experts in the room that said, but we're still 5 to 10 years away from winning Go. And that was a year and a half ago. And many of you may have heard that already the world's best human Go players have been beaten by machines, and some of the technology behind those algorithms was deep learning, or some of the stuff we're going to talk about today. Okay, so normally in a machine learning talk, I would show you, we would start talking about regression or loss and things like that. But instead, this is what I want you to think about. So I drew a diagram like this, sort of on the first day of class. We computed an expression, and I drew all the dependencies. So this is an expression too. This is the expression. I want to take the max of 0 and this expression. Doesn't matter. I just made this up. It's not important at all. But it's an expression, right? So if I wanted to evaluate this expression, I could build a processor to do so. And what I could do, if you remember our lecture from last time, I said, well, if I wanted to build a processor that could compute an OR, you know, my gates might look awfully like that last slide, right? I could have 6 inputs, and I need some output, and if this is a proper OR sequence of logic, well, whenever those inputs, sorry, if this was an AND, is this an AND or an OR? Yeah, it was an AND, sorry. So when all the inputs were 1, that's the only time it should output a 1, right? And so I said, well, if this was a table, really all input values, all combinations of 6 bits should have the output 0, except for the input 63. And if I wanted to have my circuit evaluate more complex expressions, for example, maybe a 40-bit AND, I started taking this little circuit and I hooked it up to more circuits and so on and so on. That's how I built a very complex circuit. Okay, so now instead of this little lookup table, this little 6-bit OR, I'm going to give you something else. I'm going to give you a unit, and it's going to take 4 inputs, and it's going to have 1 output. Now these are not 1-bit inputs now. Let's assume that these are floating point numbers. These are 32-bit numbers. And my unit is going to perform this basic operation. Okay? So it's going to take 4 numbers as input. It's going to multiply those 4 numbers by 4 constants. And I'm going to call those constants my weights, or my parameters. So I listed them here as W0, W1, W2, W3. And then I'm going to add in an offset, often called a bias. So that's why I called it B. So this circuit is going to compute x0 times w0 plus x0 times x1 times y1, x1 times w1, add in b, and then it's going to send all of that, the result, through another function which is nonlinear. So some nonlinear function f, and a very popular function that people use is called a rectified linear unit. Now that sounds complex. If you're not a machine learning person, you would call it max. Right? If you want to feel better about yourself, you call it a nonlinear rectified unit. Sorry, a linear rectified unit. But no, really, the reason why it is called this is because of its relationship to other possible nonlinear functions. But for the sake of this class, my unit is just going to take the dot product of n numbers with n parameters, add in a bias b, and take the max with 0. This is a single unit. Now, this lecture is called Deep Neural Networks. So I haven't mentioned the brain at all. I haven't mentioned the brain. But some people, it could be reasonable to draw an analogy. If I'm a hardware person, a unit is just a circuit. If I'm trying to draw an analogy to the brain, maybe a unit you can maybe think of as a little bit like a neuron, where a neuron gets electrical signal coming in on these dendrites. And based on some combination of these signals, it may output a signal on its axiom. So you can think about the input signals as being my x0s, and you can think about the weights as governing how this neuron responds to different combinations of inputs. So maybe, or not maybe, you could say that you can imagine a correspondence between hooking up many of these together and hooking up many neurons. And so a network of these is kind of like a network of neurons. Or you could say, I don't care at all about this relationship. I'm just going to think about these as circuits. And I know that if I have one circuit, I can make much more complex things out of a bunch of circuits. So I'm going to start chaining these things together. A third way to think about that circuit is actually as a very simple classifier. Whereas the classifier takes as input 4 numbers, and the output number is between 1 or a 0, which is the probability that we are classifying it into type A or type B. So you can think about this as a circuit. You can think about it as like a very gross approximation of a neuron. Or you can think about this as a little binary classifier that takes 4 numbers and takes that pattern of 4 numbers and classifies it into A or B with some probability output by this neuron. And to make it more clear, if you imagine that f of x was not max, but the sigmoid, and the sigmoid takes any number in the real number line, any number, and moves it into the range 0 to 1. So if the number is way over here, it's going to be really close to 1. If the number is way over here, it's going to be, the output of the function will be close to 0. And that's why if you replace f of x with this function, you can think about that unit as classifying the input numbers. You can think about it in any of these three ways. If this was a machine learning class, this would probably be the best way to think about it. Since this is going to be a hardware, an architecture class, I want you to stop thinking about any of the relationships to the brain and the classifiers. And for now, maybe just think about it as a circuit. And now we can start building more interesting things. So I can take one of these units, and I can copy it a bunch of times, and I can hook it up to other units. So now I have 1, 2, 3, 4, 5, 6, 7, 8 different units. And I hook the inputs to these units, and the output of this unit goes to all the other units. And the outputs of these units goes to this unit. So I've just made a bigger circuit. I made a bigger network. So this word deep comes from the fact that there are more than one layer to this. So I have the inputs to my function, I have the outputs of my function, and I have multiple units that take as input from other units. And each of these units, remember, have their own W parameters. So I just copied this thing 8 different times, and maybe have different parameters. So this example, so hidden layer 1 has 3 units. Each of those units have 4 weights, 4 W's, because they need 1, 2, 3, 4, plus 1 bias. So there's 15 parameters here. And each of these units takes 3 inputs. So there's 3 weights, plus 1 offset B. So there are 4 units times 3 plus 1, 16 parameters. So this network has a total of 31 parameters. And it is a deep network because there are multiple layers. And in this case, I decided to connect every input to every layer, to every unit. And every unit here is connected to every unit in the next layer. So if you hear the term fully connected layers, that's all that means. Every output from this layer is an input to a unit at this layer. Make sense? Good. Okay. So let me draw a few more networks. So here's a network, again, just like the last one, where every output at this layer is connected to every input at this layer, so fully connected. And here's a network that's actually not fully connected. So notice that this layer takes as input only values from 3 of the previous layers. This is fully connected, this is not fully connected. Okay. So now I'm going to go in a direction that might be surprising. You remember this code? This was a convolution, right? This is how we, in class, well, actually I won't say that yet. So let's review this. So the input was an image, the output was an image, and for every pixel of the output, so for every pixel of the output, we added up a weighted combination of pixels from the input, right? So for every pixel of the output here, plot over a 3x3 region of the input, and multiply the input pixel values times some weights. Remember my weights here were 1/9. And we said that this thing blurs the image. Now what if I took this code and I redrew it in terms of its dependencies? So it was too hard for me to draw the 2D array of pixels, so I just drew 1D array of pixels here. Now notice that this convolution in 1D is just 3, I'm adding up 3 elements, right? So it'd be 1/3, 1/3, 1/3. So for every pixel of output, I need input from 3 inputs around me. So I can think of the computation that I do to output a pixel as a unit. And the inputs, and it's sparsely connected to the input units, which are pixels. So can everybody see how every pixel is just a square? And the dependencies on output pixels are on 3 input pixels. If this is 1D. If this was 2D, I would draw how many arrows from this side to this side? 9, right? Okay, good. And that's like, I'm showing that as well here. So here's the output color. This is the corresponding input pixels. Now, we didn't talk about this in our image processing lecture, but I could also say, you know what, I don't want to compute every output pixel. Maybe I want to compute every other output pixel. Or maybe every 3rd output pixel. So I'm going to just get rid of some of these pixels. So if you look at the code, I'm going to make one change here, is that I change this to stride. So stride is 2. So now instead of producing every output pixel, I'm producing every other output pixel. So notice that with stride 2, so 0 gets its inputs from 0, 1, and 2. Then I need to produce pixel 2, and that will get its inputs from 2, 3, 4. All I did was just say that the output now is not the same size as the input, it's half the size. Just stride 2 convolution. Okay, so now let's think about things. So, what does convolution with these weights do? Those weights are 1/9. Or in other words, what does this code do? If I have an input image, how would you describe the output image? Somebody help me out. If I have an input image and I run this code and I look at the output image, what would it look like? It's going to be blurry, right? Exactly. Okay. So that's the answer to this question. What does convolution with those weights do? Because it's going to take an input image that's nice and sharp. That's the zoom view. And it's going to produce an output image that's blurry. Here's another question. Might be a little bit trickier. What does convolution with these numbers do? Talk about it with your friend for 1 second. Okay, I heard a word whispered by many people. What was the word? I heard Gaussian. But that is not the answer to my question. I asked you, what does this filter do? And you said Gaussian. That does not type check with the question. So what does the filter do? It is actually, if we want to be precise, a discrete approximation to a Gaussian kernel. Correct. But what does it do? Sorry? It's a blur, or if it would low-pass filter the signal, which is another way of saying a blur. So yes, if I convolve, don't change the code at all, but I use these weights, I get out this blurry result. Now, if you are thinking, wait a minute, Kayvon, you just already did that. It's a little different. So let's take a look at, so if we look at box, so all the same weights, if you look here, there's still a little bit of structure. Like you still see a little bit of pattern, right? And if I smooth it with the Gaussian kernel, it's actually much smoother. You don't see those edges anymore. So for those that are not related to this lecture, but for those of you that are interested in signal processing, the Gaussian filter will eliminate most of the high frequencies from an image, whereas a box filter will not. And that's all I will say on that. I could give 4 lectures on that in different classes. Okay, so now here's a new question. What do these filters do? There's negative numbers now. So talk about that for a second. Okay, so what does this one on the left do? And here's the trick that I like to think of, is when will the value be the largest for a pixel? Can you describe to me what the inputs look like to make the output of a pixel like the maximum value? So think about the convolution. What pixel, what could I do to make it really, really bright? Yeah. So I need to take a negative number here and a big positive number here, right? So if I had an image that had all of this region had negative numbers, and all of this region had positive numbers, then a pixel right here would multiply the negative number by a negative weight and add the positive number plus the positive weight. Or equivalently, if I said what will give you the maximum absolute value, really this filter here is going to correspond to big differences between pixels in this direction. Right? So in other words, it's going to actually respond to large horizontal differences. Or in other words, actually like a vertical line. And what about the other one? It's going to be, it wants to look for very large vertical differences. So if I run these filters on that same image, let's think about what I get. I'll get, for the first one, I'll get things that light up, pixels light up, whenever the pixels over here are very different from the pixels over here. And that's vertical lines. On the opposite case is true here. Now I have pixels lighting up, where the pixel above it is very different than the pixel below it. And those would have been horizontal lines. So even though I told you, we started thinking about filtering images as blurring them, if I just change the weights, now I can think about convolution as something very different. It's actually detecting a particular pattern in the images. And in this case, I made a filter that detects vertical lines, and I made another filter that detects horizontal lines. Everybody see that? So I'm not image processing anymore, I'm analyzing images. So now, let's say that this is my image, and it's of size width by height. This is going to be a new picture. Imagine that I want to convolve that image with one filter. And that filter was 3 by 3 numbers, right? And so I'm going to write that 3 by 3 block as just one of these things right here. And if I take an image and convolve it with a filter, I get a new image. And now I'm going to say, I'm going to convolve that image with many different filters. In fact, num filters of them. So I'm going to take an image, pick some weights, run a convolution, get an output image. Then I'm going to use a different set of weights, convolve the image against that new set of weights, and get a new output image. So if I do that, this is exactly what will happen. So here are my weights. My filter weights are just ones and zeros, and I'm actually just showing you a picture of the weights. Whereas if we go back, just to be really clear, if I wanted to draw this as an image, this filter would look like let's say really dark, gray, and really light. This look like if I actually visualize the filter as an image. So filters, notice that that filter that used to look for horizontal lines, that looked for vertical lines, actually looks like a vertical line itself. So filters end up detecting things that look like them, because a convolution is just a dot product. And so dot producting this image with various parts of the image is it'll respond the greatest when the image looks like it. So that's what I did here, is I took 96 different 11 by 11 filters, not 3 by 3 anymore, 11 by 11. And I convolved all 96 of these filters against this picture of me. And I got out 96 different outputs. Now one little detail here is that these are 11 by 11 by 3 filters, because they're now running on an RGB image. So I have, every weight is not just a scalar, but a vector of 3 numbers. So that's why it's not just 11 by 11. Imagine that there's 3 numbers here, 3 numbers here, 3 numbers here, and so on. So if you understood the previous slide, which said that filters detect things, then each of these little images are how much of that pattern there are at various points of the image. So this being white suggests that at this point in the image, there's just a lot of gray. And with this filter, this means that whenever this filter is bright, there must be a lot of vertical lines this way. So maybe it's this or this, it's hard to tell. So that's the output of running 96 different filters against this image. So I'm going to represent that in this way. I have an image that's width by height. I have all of these different filters, so I'm going to represent them as 3 by 3 by number of filters. Or in my previous diagram, it would have been 11 by 11 by 3 by 96 filters. So since there's all these weights, and I want to think about a bunch of filters, if I think about there being another filter with more weights and another filter with more weights, that's why I'm drawing it like a volume. It's common to draw it like a volume. So one image times 96 different filters gives me out 96 different new images. And that's this one. Now I can do things to those images, like for example, I can multiply every pixel by the max function. And remember, max is the same thing as the magnified linear unit. And I can do things like downsample the image later on, shrink it to something smaller. So I've given you 3 different operations. Take an image and convolve it. Take every image and then just multiply all the pixels by max. And one more, which is take an image and just downsample it, or compute the maximum value in every 2 by 2 region. These 3 operations are all I need to do some very sophisticated things. And so I want to remind you that, what did we say a unit was? So a unit was the dot product of the inputs with the weights, plus a bias, and then that value sent through the max. What is a convolution? A convolution at every pixel is the dot product of the input pixels and the weights to get an output pixel. So you can think of there as being a unit every time you have a convolution. So in other words, this is another way to represent this convolution here is like saying there are 96 different units processing all of those pixels. So now I have my first deep neural network. It takes this input and image, and that image is a size 224 by 224 by 3 RGB. And for every one of these pixels, I'm going to run 96 different filters that are of size 11 by 11 by 3. And I showed you what those filters were back here. And I'm going to get out 96 images. Those 96 images are represented right here that are of size 55 by 55. So that 224 by 224 image turned into 96 55 by 55 images. The reason why 55 by 55 and not still 224 by 224 is because we went by a stride of 4. So we computed the convolution for every 4th pixel. So we divided 224 by 4, and so now it's just a 55 by 55 output. So input image 224 by 224. I ran 96 convolutions, so I got 96 output images. And they look exactly like this. And now, just like I can think about an RGB image as an image that actually has 3 images, a red image, a blue image, and a green image, I can think about these 96 outputs as just one image, where every pixel has 96 dimensions, or 96 channels. Imagine I put all of these right on top of each other. So that's what I'm showing right here. 96 images of size 55 by 55. And then we're going to take those 96 images and we're going to run 256 convolutions on them. And we're going to get out 256 new images. And then we're going to do it again. We're going to run 384 convolutions on them and get out 384 images. And then we're going to run another 384 convolutions on those images to get out 384 more images. And we do it one more time with 256 more convolutions. And then, finally, we're just going to have every input go to every output twice. And so when you see, this is the deep network that for computer vision got a lot of things going. It's called AlexNet because a grad student named Alex Shishevsky came up with this network and shown that if you did this, this was a very powerful network for detecting patterns that allowed you to classify images into what's inside the image. Like, is this a cat or a dog or a car? So if you're thinking at this point, this doesn't really make much sense. How could continuing to run convolutions on an input image ever end up with this is a dog or a cat or a car? I think that's a very reasonable reaction at this point. Because the only thing I have told you is that, hey look, we're going to run thousands of convolutions on the images, and then we're going to run convolutions on those, and everything is going to work out okay. So let me try and help a little bit. So here's another example where this was 5 convolution stages. Since then, we have networks. In 2015, somebody else came up with a network that did 16 back-to-back convolution stages. And these days, we run networks all the time that do like 124 back-to-back convolution stages. So they're really deep. So people were like, what in the world is going on? How is this working at all? And so some folks made some very interesting visualizations that begin to kind of shed some light on what's happening here. So let's think about what this network is doing. Oh shoot, I actually have. I'll show you guys after class. I have an interactive version of this that I wrote myself, and I'll show you afterwards. Maybe I'll get it up during the break. So here, what's going on here is that, remember when I asked you, what pixel pattern do you think will make those filters on the screen the most, will give the highest response? And we said, oh, well, if we had a pattern that had really strong vertical edges, that will cause the output of the convolution to be very high. So what is being visualized here is for 9 different filters. Remember, there were 96 of them. But for 9 of them, these are the input images on a big data set that cause the convolution to give the highest output. So notice what you can see about this particular filter. How would you describe, this filter? If our earlier filters were about responding to horizontal edges or vertical edges, if you had to describe to me what this filter does, what would you say? It detects green, clearly, because green things give it the highest response, right? So if I had to design a filter that detects green, well, I can think of one of them, like let's say it's this big convolution. And it's 11 by 11 by 3. Well, if it's detecting green, it probably wants a really high response, some constant C to red, some really, high response to blue in the same position, and probably no response at all, to green in the same position, and no response at all to blue. This filter seems to respond to orange-white blobs. And this filter seems to respond to greenish lines in some vertical-ish ratio. Okay. So if this is a good description of the pixel patterns that the first filters respond to, let's think about what happens when we give those output images, when we give these images. So one of these is how much red there is, and another one is how much vertical lines there are. Now remember that the next set of filters are convolving these things. So if each of these tells me how much orange blob there is, or how much green there is, or how much vertical line there is, the next filters say, layer 2 says, well, I want a lot of green and a lot of orange vertical blob. Or I want a lot of green next to no vertical blob, or something like that. So these are the pixel patterns that trigger the second image. That's the second level of features the most. And notice that we've gone from lines and small simple patterns to slightly more complex patterns. Because these new convolutions are responding to a little bit of vertical line and a little bit of horizontal line, plus maybe some red blob at the bottom. And then if we do it again in the next layer is now responding to a little bit of horizontal line, a little bit of vertical line, a little bit more horizontal line. And you're starting to see more interesting patterns begin to emerge. So this is clearly a filter that responds to like a honeycomb or a checkerboard pattern. This is clearly a filter that corresponds to round orange things. And if we keep going down the network, you see that the responses start becoming more and more combinations of the previous stuff. So now all of a sudden we have things that look like pretty clearly dogs, because maybe it's responding to brown, white, green, and some round things that look like eyes. Notice that almost all of these dogs tend to have green in the background. Here's an example of very roundish, circular things. And then by the time we get to layer 5, everything is very, things are starting to get much more complex. And you can look at it and go, oh, well that must be the filter that really responds to dogs. So the power of these things is coming from the depth. It's every step you're combining things that make a little bit more meaning, a little bit more complex, into more complex things that you can understand better. So more recently, so I've been giving you, an example of 5 stages, but that was a long time ago. That was 2012. And deep learning is moving very quickly. In the last 5 years, the more modern networks, so here's a network created by Google, which has many stages. Here's a 34-stage network. And so depth has been shown to be useful. You want to just take the outputs from the previous layer, mix them together in new ways with convolution, and continue on. So the way to think about this is that deep networks learn useful representations. I didn't know that it was useful for vertical lines to be combined with blobby red things and a little bit of round green things to solve my object classification task. But this network has decided that that's how it's going to solve the problem. So in some sense, these filters have learned by setting the weights, they're picking out the things that are important to solve a particular task. So at this point, you're like, okay, I kind of maybe see how this might work, but you haven't told me where I get these parameter values. And I'm not going to tell you where I get the parameter values, at least until next class session. So I want you to assume that these weights are given. And now let's talk about how we can efficiently start implementing some of these deep networks, now that we know, at least we know what they're going to compute. So how many of you know what matrix multiplication is? I'm assuming everybody knows what matrix multiplication is, right? So I'm going to go ahead and write it in code for you. Here's my basic C code for matrix multiplication. Pretty simple C code, right? I have a matrix C, it equals matrix A times matrix B, and for every output element ij, I'm going to take the dot product of a row of A and a column of B. Basic. So here's my question. Now I want you to think about your high-performance programming knowledge. And if I ask you what is the problem with this implementation, or in other words, why is it slow? Does something like bother you about why it's slow? If you wrote this code and you compiled it, even if you put a pragma openmp parallel 4 to parallelize it onto many cores, I guarantee you I could write a better version of matrix multiplication that was at least 1,000 times faster. Even on my laptop, 1,000 times faster. What am I so unhappy with in my program? Many parallel programming classes make this an assignment. Multiply matrices as fast as you can. I don't do it because it's boring. How would you make it faster? It's already parallel. Yes?
Rotate the matrix B.
So you're going to rotate the matrix B. So first of all, what is the motivation for your approach? What problem did you identify that you want to fix?
This implementation is like our locality.
Yes.
Because matrix B, because when I sense matrix B is like our locality, so I want to rotate it.
Correct. So you were concerned that, well, if we have plenty of parallelism, what is going to slow us down? Data access is going to slow us down. So let's go look at the data access for all three of the matrices. So let's start with matrix C, because it's on the left. So matrix C, I write to it right here. and I write to it ji, and I'm iterating over j, and then I. So I'm going to write to matrix C every once in a while. And I'm going to write to it in this order. Perfectly cache-friendly, in order, no problem at all. And then at the end of this, so when we come back, I will I'll pick up and we'll talk about what's good with A and bad with B. Okay, so we take a 5-minute break. Okay, so I forgot about this demo earlier in class. So here's a little web page that I made. Now what I did is I ran like 100,000 images as input to the AlexNet deep network. And what I did was for every filter in layer 0, and remember there's 96 of them. Let's make sure. Yep, 96. I stored the images, the pieces of the image, out of 100,000 images, which pieces gave the highest response to that filter. So if we thought about these 11 by 11 filters being convolving over all these different images, at some point the filter gave a really strong output pixel. And so I saved the input pixels that caused the output. And I saved the top 16 of them. So notice that for the first layer, these are 11 by 11 regions that cause the strongest response. So this filter is clearly the one single large white line filter. This is the green filter. This is the multiple black lines filters. But what's more interesting is what happens when we go to the next layer. So now you see larger filters. Because remember, the reason why it's a larger filter is that, so if filter 1 is just like 11 by 11, and then I filter again. So I filter again, I forgot what level 2 is, I think it's like 5 by 5. So now I'm taking like 5 by 5 of 11 by 11. So 2 filters is like looking at a much larger region of the input image. So this is that region of the input image. So clearly we have like the spiky grid filter. We have the blurry white thing filter. We have filters that look for strong edges. Filters that look for patterns. Filters that seem to respond to text. Circles. And then I bet if we go to layer 3, you're going to start seeing even more interesting patterns. Oh, look. So how many filters are at layer 3? I think there's 256. No, there's 384, right? Yeah, there's 384 filters. So, okay, so there's a filter that seems to respond to cute fuzzy things. Ladies. Sometimes. What else? Coke cans, circles, men and cameras, dogs, small red things, feet. And then if you just keep moving up, oh, brakes. No comment. So we can move all the way to 4. It's kind of similar at this point. There's a lot of calculator filter. Anyway, so you can kind of see how something interesting has been learned. Definitely with the people, dogs, Okay, well I'll stop there for now. I'll put the link on the web so you can look at this. This is just one of my web servers back at CMU. But there's some pretty interesting patterns. Okay. Okay, so we were talking about matrix multiplication when we left off. And the problem was that even though we were reading through memory nicely in the right order for C, and nicely in the right order for A, we're actually reading through huge steps in memory in B. Because B is stored in column in row major order, and we go from one row of B to the next row of B. We only read one element from the cache line, and we might jump really far. So almost all of the accesses to B are cache misses. So the suggestion, so one solution would be to fix the problem by I thought I put a B transpose. Oh, okay, sorry. So one solution would be to transpose B. So if I just transpose B to BT, B transpose, then I can run through B very, very efficiently. I can make use of my cache lines really well. But there's actually an even better solution. So I like that solution. But there's actually an even better solution. And the better solution would be to change my code so that, so transposing B just means that I'm reading through memory very efficiently. But I'm still reading from memory. And what I would like is every single time I load items from B into memory, or items from A into memory, I'd like to use them as much as possible by reusing them from the cache. So I can do that by changing my loops. And what I've done now is I said, okay, what I'm going to do is I'm going to read a few elements from A, a few elements from B, and then I'm going to read a few more elements underneath it from A, and reuse the elements from B. And a few more elements underneath it from A, and reuse the elements from B. So now, whenever I load a red block of data into the cache, I will use it until I don't need it anymore. So each of these little computations here is a little submatrix multiplication. So here's a question that I want you and your partner to think about. So it makes sense that I'm going to choose block size so that this amount of data from C, this amount of data from A, and this amount of data from B all fit in cache at the same time. But I have this question down here at the bottom. Do I want as big a block size as possible, or as small a block size as possible? I want you to think about that for a quick second. So I'll give you 20 seconds. Do I want to make block size as big as I can, or do I want to make block size as small as I can? Think about that for 1 second. Okay, so who thinks I want to make it as big as I can? I want to make block size as big as I possibly can while keeping the matrices in cache. Okay, who thinks I should make it as small as I can? Nobody thinks anything. That's not good. Okay, so it's a binary question. You have to raise your hand. Who thinks block sizes should be as big as possible and keeping the matrices in cache? Okay, a few people. Who thinks block sizes should be as small as possible? A few people as well. Okay, so those of you, since the majority thinks it should be big as possible, can somebody give me an explanation why? What is the benefit of making block size big? You have an answer, and it actually happens to be the right answer. So Why did you come to that conclusion? Why did you come to that conclusion? I'm going to start calling people today. Okay, who's going to help me? I'm going to go to you guys over there. You were very confident, I can tell. So you all said it was going to be as big as I can make it. Why did you say that? That was correct.
Because I think if the block size big, you can load elements that you want to load them many times.
Okay. So you want to load them, yeah, you want to use them and as many times as possible.
Yeah.
So let's think about this. So what is the complexity of matrix multiplication? If I have B by B blocks, let's just say they're square. Well, that means I need to load B squared data, and I have to load it 3 times, A, B, C. How much computation, how much work do I have to do to multiply 2 different B squared blocks? What is that? B to the what power? 3, right? So I have to do B cubed computation. Now in this class, we know that the magic number is how much computation compared to how much data we read. Right? Many of your homeworks have had you think about that. So the ratio here is what? It's O of B. So the bigger my blocks get, the more mathematical operations I can do for every number I have to read. And so I'm less likely to be memory bound. So I want to make my blocks as big as possible as long as they fit in cache. Right? So my matrix multiplication, this was my code for one level of blocking. But I actually might block for the L1 cache, the L2 cache, and so on and so on. So this code, which was 4 lines of C code, if I asked you to write this algorithm properly, it might more look like this. And we haven't even talked about parallelism or SIMD yet. So, maybe if I wanted to multiply 2 matrices, I would want to start SIMDizing the thing. So if I wanted to do SIMD, I could say I want one 8-wide chunk of C to be multiplied against one element of A times a whole vector of B. And that's sort of what I did here. And the details of this code are not that important. What is important is you might agree with me that it's starting to look a little messy. And we can play tricks. Like there's another version of it where I could use your trick of transposing B. And I could get something else that looked like this. Where now I'm running horizontally through A and horizontally through B. But I have a little problem because I now have a dependency in computing this dot product as I go. And so if I really care, I might remove that dependency and might go with some other implementation that transposes A and C. And the reason why I'm going fast is not that this is really important, but because I can make an entire 2-week assignment off of how to write matrix multiplication really fast if you wanted SIMD and multicore. Now, why am I telling you any of this at all about matrix multiplication? Now I want to tell you how to implement convolution using a matrix multiplication. So imagine that we want to convolve this input image X. This is a picture. We're going to convolve it with a 3x3 filter with some weights. And since it's 3x3, I've decided to have 9 weights. So imagine I gave you a really fast matrix multiplication. So if these are my weights, and I know that the output at pixel 0, 0 is going to be these weights times some of the elements of the input image, well, I can copy the appropriate elements of the input image into a row of this matrix. And then for the next output pixel, I could copy another set of elements. So these elements go into this row of the matrix. And these elements go into this row of the matrix. And around x equals 1, 1, these 9 elements go into this region of the matrix. So now notice that if I took this matrix, which is width 9, and height, the number of pixels in the image, and I multiply it by this vector, which is just a small little length 9 vector of all the weights, the output is the result of convolving these weights against that image. So I've reduced convolution to matrix vector multiplication by copying values from the image into this special matrix. Now notice that this matrix is 9 times bigger than the original image, because every pixel I copied 9 times. So if you look at x1 appears 3 times, and if I kept going, you would see it 9 times. So if you didn't want to bother writing really fast convolution, because it's very difficult, because it can be difficult, but I gave you really fast matrix vector multiplication, you could copy your input image into this form and have a very fast convolution at the cost of 9 times more memory. Now what would you do if I said I wanted to do 96 convolutions against this image at once? Can you describe to me how you would change the matrix or the vector? If I wanted to do 96 convolutions, I don't want one vector as output. I want 96 vectors as output. So I want a matrix as output, right? So how would you change my math here to do 96 convolutions at once? Would you change the matrix? Would you change the vector? How would you change the vector? You would add columns, right? So if I want to do 96 convolutions at once, or number of filters at once, I just stack up those extra weights. And now all of a sudden, I have a matrix-matrix multiplication problem. And this can be made really, really fast, because matrix multiplication is like one of the fastest things that is written for modern computers, because it has O of B work per unit memory access. So it's never memory bound. It's very, very efficient. Now, quick question. What happens if the input image is not one channel, but let's say it's RGB? Just as a check your understanding, if I wanted to convolve against an RGB image, how would I change this? Does anybody see? It's not going to get longer because there's only width by height pixels. It's going to get wider, like this, right? So now the output at every pixel is going to be the red values convolved with the red weights, plus the green values times the green weights, plus the blue values times the blue weights. That's why the convolution is 3 by 3 by 3. And of course, if I wanted to do this, right. So this is how I can express convolution with a lot of filters, and a lot of multidimensional filters, as really efficient matrix multiplication. Except I have copied my input image all over this matrix and wasted a lot of memory. And these memory footprints can get quite big if we think about a network with a whole lot of layers. So for example, consider one layer that has 224 by 224 image outputs, but 64 of those filters. Well, that's 12 megabyte output matrix. And sometimes we run these on 1,000 images at once. So if we run a deep network on 1,000 images at once, that might be a gigabyte of memory to actually, or 100 images at once. That could very quickly become a gigabyte of memory to hold the output. So many early implementations of deep networks, like if you used Café or early implementations, they would implement conv layers as a big dense matrix multiplication like this, because that was really fast code. Now, because of how much memory they were wasting, modern implementations don't do this. They say, I'm going to implement the conv layer directly as it would look like in code. So for every image in a batch, or for every pixel, input and output pixel, for every filter, convolve the filter against the input image. And so this is the loop nest for a convolutional layer and a conv. Now remember I told you that the 3 loop nest matrix multiplication would be a good 2-week programming assignment to make it go really fast. Now all of a sudden you have a 7 loop nest that you need to parallelize. And that's what, if you use modern deep network libraries, there has been people that have gone off and spent a lot of time taking this very, fairly simple looking code and spending months or years tuning that for modern processors like CPUs and GPUs. And that's what you'll get on a GPU if you use NVIDIA's framework called cuDNN. And that's what you'll get on an Intel processor if you use Intel's framework called MKLDNS. Just as a note, this is the implementation in Halide, but I'll skip that for now. Okay. So one way to make convolutional layers go fast is to optimize that code above. But there's increasingly more interesting ways to make it go fast. So for example, those of you that are familiar with signal processing know that convolution can be performed efficiently in the Fourier domain. So some implementations of these convolutional layers transform the input into the Fourier domain, do the convolution there, and transform it back. Another popular way of implementing the convolution is similar to a fast Fourier transform ideal, and it's called a Winograd convolution. So here, let's think about if it was a 1D problem. Let's say I have these 4 input values, and I want to convolve 3 elements to get 1 output, 3 elements to get 1 output. So here I rewrote it as a matrix problem, just like I showed you on the last slide. Is that the output y0 is just the dot product of x0, x1, x2 dotted with the 3 wings. And y1 is the dot product of x1, x2, x3 dotted with these 3 wings. So if you just look at the math in this thing, you can find common sub-expressions. And you can tell that, well, y0, well, yes, it is equal to x1 times w0 plus x1 times w1. But it's also equal to just the summation of these 3 values, these m values, where these m values are derived here. And some of these computations are dependent completely on the weights and actually can be pre-computed. So now I can actually compute this, where if I did this using normal convolutions, it would be 6 multiplies and 4 adds. Whereas here, I can do it with 4 multiplies and 8 adds. So in this case, I didn't reduce the total number of instructions, but I reduced the total number of multiplies, which can be important in sort of FPGAs and hardware. If I showed you the 2D version, it would actually reduce the total number of instructions. So this is an algorithmic change to the convolution, which gets you the exact same answer, but leverages common substructure in that matrix multiplication. And it's pretty cool. Now, remember last week, or maybe it was 2 weeks ago, we talked about, oh my gosh, every single time I read a value from memory, I could have done hundreds, sometimes even thousands of math operations. And I also told you that these early deep networks had many, many weights, many, many parameters, because they did convolutions after convolutions after convolutions. And I may not have stressed it earlier in this lecture, but for example, that 7-stage network that I told you about had 68 million parameters in it. 68 magic numbers. That's about 260 megabytes of data if those are floating point numbers. So if I had to actually run that network on a video stream at 30 frames per second, well, that's about 1.3 watts of power just to read the weights, just to read the network. 1.3 watts of power cannot be, that's the entire power budget of my phone in most operations. So there's a lot of work that's going on trying to make these networks much, much smaller. And so the original footprint of these networks, 200 megabytes, 500 megabytes. Maybe a bigger network is a billion parameters. And so some people have looked at this stuff and said, well, if we look at those weights, well, if some of those weights are near zero, that means that they don't impact the final solution very much. So why don't we just take the weights that are near zero and let's just get rid of them. Let's just ignore that input completely. And that'll be a way to compress a deep network. So let's just take all the really low values that don't matter too much anyways, and let's make them zero. So that's what these folks at Stanford did. And they showed that, well, if you sparsify the weights, and then you compress the sparse representations. So if this was your weights with a lot of zeros, you can easily compactly store that as index comma value, index comma value. You can reduce the storage overhead of these indices by encoding just the difference between consecutive indices. So if the non-zeros are 1, 4, 9, well, we can encode that as 1 plus 3 to get 4 plus 6 to get 9. And the deltas are much smaller. Then they went even further, and they said, you know what? For every set, like if this is a filter, I'm going to be even smarter, and I'm going to cluster all the weights, and I'm going to clamp all the weights to one of 4 values. So I'm going to compress this data with a lookup table which says every weight is just one of these 4 numbers. And they derive the numbers by looking at the weights. So they started doing all the basic data compression things that you would see if you were a data compression person. So they worked really hard to compress these things. So I'll skip this. But the point is that they were able to take this network, and remember this network used to be, I think it was 500 megabytes. They were able to reduce, the original was 138 megabytes, a million parameters. They were able to retain only, 3% of the parameters. So they wrote a code that compressed the network to 3% of its original size. And that was pretty interesting. Now, many of the newer networks, like networks that are run by big companies like Facebook or in particular Baidu, they're actually much smaller. They're actually just as powerful, but they can get by with like 7 million parameters rather than 138 million parameters. And just last week, or not just last week, just last month, there were some papers that published new networks that were designed to be really fast and small for mobile phones. And these mobile phone ones are saying that, look, compared to these old networks, these new ones are about as accurate. They get the answer right 70.6% of the time as opposed to 71.5. But we've reduced the parameters from 128 million down to 4.2 million. Right? That's about a 40x speed up with just a better algorithmic design. Same thing here is, if you're willing to sacrifice accuracy down to 60%, you can get all the way down to 1 million parameters. That's only like it's 4 megabytes. So it's interesting to see how in the last 2 years alone, as deep networks have become more and more popular, it's people designing better networks have given us 10, 20, 30x speed ups, not necessarily building 20, 30, 50 times faster hardware. So a lot of the innovation is coming from smarter and smarter algorithms. Now, of course, we still have to run them really fast. And almost the fastest programmable machines on the planet have typically been GPUs for running these deep networks. That's why it's very hard or very expensive to buy Titan X Pascal GPUs for gaming, because everybody's buying them to do AI and deep networks these days. Now, GPUs are efficient, but we care about even more efficiency. And so that's why you're starting to hear news, because this is so important to so many people, of people buying ASICs, or sorry, building new ASICs to do evaluation of deep networks, essentially to evaluate these conv layers that we talked about. So one of the most publicized efforts is the one by Google, which in their data center every day are using specialized processors just to evaluate deep networks. So this is an example of that processor. Here's a board in the data center with 4 of those processors, TPUs, tensor processing units. Intel has announced plans for their own ASIC, and there are many startups, in particular many startups actually in China. There was a very interesting article this week about them, that are all trying to design different forms of new hardware to be ASICs for different types of deep learning. And almost all of those are there to accelerate conv layers. Conv layers and these things called RNNs. So so there's GPUs, Intel, FPG, like everything we've talked about in class so far is being thrown at this problem. And there are also some very interesting domain-specific languages and frameworks that are popping up to help make it easier to write deep networks. And those are things like TensorFlow or Torch or Caffe. But even though we're starting to get some domain-specific frameworks, I personally think that the state of affairs is quite primitive. Like the way this is a network created by one of my students, and it's not even a single line anymore. In fact, he's experimenting with how to put if statements into networks. So instead of just evaluating convolution after convolution after convolution, you might say, oh, based on these outputs, I think these are the filters I should run instead of these filters. And basically, this is like assembly language programming. It's not very fun. And so I think that there's still a lot of work to be done in programming languages for deep networks. So that's the first part of today's lecture. Let's take a quick break. Let's take a few-minute break. And I'll come back with a little lecture on some of the issues in training these things. Okay, so we'll take a quick break. So I will keep going through the bell, though. Okay, so let's talk a little bit about actually learning these parameters. So here's a question for the audience. How would you describe the professor in this photo? Right, so there are four classes. You can describe the professor as easy, mean, boring, or very nerdy, right? So, it's a hard problem. But imagine that we had a classifier. And a classifier is a function that takes as input, let's say this image, and it's going to, as output, pick which of the 4 categories is most applicable to the professor that is in the image. Now, it's not actually going to say which professor. What it's going to say is it's going to output, let's say it's going to output a probability distribution on how likely it is that the professor in the photograph is of those 4 categories. So the input is an image, and the output is actually going to be a vector of 4 numbers, which are the probabilities for easy, mean, boring, nerdy, and so on. And this black box is going to be one of these deep networks that we talked about. Now, recall that these large networks may have tens or hundreds of millions of parameters. Now, efficient ones may only have a few million parameters, but we have millions of parameters that we need in order that we need to set so that if we input some image, we do all these convolutions, all these convolutions, all these convolutions, and then what comes out the very end is a probability distribution that makes sense. So in this case, the output of this network says that there's a 52% chance, or 52% confidence, that that professor is a nerdy professor. Now, the question is, well, how do we magically set these 10 million or 100 million numbers so that comes out to be true? So how are we going to do that? I have a million magic numbers. If I get them all to the right values, in other words, if I set all the convolution weights just the right way, when I produce, when I send this black box a picture of a really, really easy professor, well, it should probably say 0.99000. So here's how we're going to do this. So if I taught you something, if I have to teach you in class, usually I like to give you a bunch of examples. I don't just talk about things abstractly. I give you an actual example. I say that if you need to learn how to do something, here's one practice problem. Here's another practice problem. And I give you the answers to those practice problems. In fact, I'll give you the answers to practice problems 3 later today. And so let's say that I gave you the answers to this particular problem. So these are a bunch of professors at CMU. Maybe others will come and give lectures here too. And let's just say that there was a database that students created where they gave every single one of these pictures a label. There are sites like ratemyprofessor.com, those kinds of things. And in fact, students do give professors labels all the time. So, and in this case, I've decided to label all of the pictures of B as a nerdy professor. So let's just say that the world agrees that if you see a picture of me, this network should classify that as a nerdy professor. So let's say that a picture of me comes in, and notice that this picture of me is different from all these other pictures of me. Right? There's one, this picture does not exist in this data set. But it's a picture of me, and the network was told that the right answer is that whenever you see Kayvon, that's a nerdy professor. So let's say that this image comes in, and the output of the network, or the right answer, should have been 0001. Because Kayvon is a nerdy professor, means that that's the right answer. But the network actually produced this output. It actually was fairly close. So we need a way to change the parameters just a little bit so that the output is much more close to the actual answer that we want. And so we need a measure of how wrong the network currently is, and that is usually called the loss. How much is the network wrong? And so in this case, if this is the right answer, and this is the answer that the network produced, I need to compute the difference between the right answer and the actual answer, and that's the loss. Now, that loss we can think about as just being like an L2 distance on vectors, but a common loss is this softmax loss. And a softmax loss is well, I don't want to go into too much on why this is a reasonable loss function, but we can look at this and gain some intuition about what it's doing. So the softmax says we're going to take the value of the correct category. So the correct category here was nerdy. But I only gave it 0.52. So I'm going to exponentiate that value. And I'm going to divide it by the sum of all the other categories. So think about it as if the output of the network was 100, what would the loss be? It would be log of 1, which is 0, no loss. Makes sense. If the output of the network was 0 for the nerdy category, and 1 for some other category, what would the loss be? It would tend towards negative infinity, right? Like if I was very confident that this professor was not nerdy at all, this would be the log of something close to 0 over some other number, which would move to negative infinity. So the softmax loss is doing something very intuitive. If you stand up and say, this is definitely this, and you're wrong, you should get hit really hard. So the loss is high. So we're penalizing really confident wrong answers, because that's the worst case scenario. We would rather be kind of 50-50 than saying, I am completely right and this is the answer, and being wrong about it. So that's what the softmax loss is doing. And of course, during training, I'm going to give a whole bunch of examples. The network is going to output its answer, and I can compute the loss for all of those examples, and I can just add them up. So if Li is the loss for the ith image, L is just the sum of all of those losses. Okay, so imagine you have a loss and it's not 0. That means that we can do some more training to make the network better. So how are we going to change the parameters to reduce the loss? Well, one answer is if you have loss, you can randomly choose one of those 100 million parameters, and you can tweak its value a little bit and see how it went, and keep tweaking the values randomly. And hopefully at some point, you find some magic set of 100 million values when the loss is low. But in fact, there's much smarter ways to do this. Right? So to give you a little example, let's imagine we have a simple function here, and it takes 2 parameters, p1, p2. And let's say that we want to set those parameter values so the function is 0. We want to minimize the function. But with the current values of p1 and p2, the function outputs 10. And now let's assume that I also gave you the derivative of the function with respect to those 2 parameters. df dp1, df dp2. So df dp1 is 2, df dp2 is -5. Or in other words, I'm giving you the gradient of this function. So if you wanted to make the function 0, how would you change the parameters, given the information in these derivatives? What do these derivatives tell us? How should we change P1? We should make it bigger. We should make it smaller, because we know that if we make it bigger, the function's value will go up. If we make it smaller, the function's value will go down. How should we change P2? We should make it bigger, right? Because that will decrease the value. And if I had a choice between changing P1 or P2, which one would you choose? P2, because it's more sensitive to P2. So in other words, what we're doing is we're saying that if this is a plot of the value of f, where blue is 0 and red is a high number, and my current values of P1 and P2 put me here in P1 and P2 space, I just need to walk in the direction of the negative gradient. So the derivatives tell me how I should change the parameters to get closer to my target output. Or in other words, if I have a loss and I want to make that loss 0, the derivative, the gradient of the loss, tells me how to change the parameters. So this is our basic training procedure. While the loss is too high, for each item in the training set, so for every image, evaluate the loss gradient. So compute the gradient of the loss, and then adjust the parameters. So this is a vector of parameters. Adjust the parameters by the gradient, times some step size, which means how much you want to walk in the direction of downhill. So the only thing left is how do we compute this loss gradient with respect to millions of these parameters. And this is where your algebra from high school, or maybe before high school, comes in. Or not your algebra, your calculus side. So imagine we just had a simple function here, like f of x, y, z. Now I'm going to rewrite it as, so it's x plus y times z, and I'm going to rewrite it as a times z. So if I ask you what the derivative of f with respect to a is, well, you wouldn't hesitate at all. You would say, well, the derivative of AZ is very much Z. The derivative of AZ with respect to A is Z. And the derivative of A with respect to X and Y, well that's 1, right? Since A is X plus Y, then the derivative dA dx and dA dy are 1. Okay. So by the chain rule, back to high school, is the derivative of f with respect to x is the derivative of f with respect to a times the derivative of a with respect to x. No problem here either. So the df dx is just z. df dA, z times dA dx, 1. And it actually makes a lot more sense when thinking about neural networks to draw this out as an expression. So here's the expression for this function. And on the outputs, I'm putting the value of this sub-expression. So z is 5, y is 4, x is 3. X times y, or x plus y is 7, and the total output is 35. Make sense? So now we're going to go backwards in computing this gradient. We're going to do this very mechanically. So what is the derivative of f, sort of with respect to f? That's just 1. And so if I have inputs to f, if I change this number just a little bit, so this is the value a, right? Because a is x plus y. So if I change a just a little bit, well, whatever I change a by is going to get multiplied by 5. Because the output is going to be a times 5. That's the output of that. So if I change a by 1 unit, f is going to change by 5 units. So df dA is just 5. If I change z by 1 unit, well, the amount of the output change is going to be 7. So df dz is just a, which is 5. Let's keep going. So let's just say if df dA is 7, and I change x a little bit, well, how much does a change? Well, if I change x a little bit, a changes just by 1 unit. So that's dA dx. Well, then df dx is also 5. Because df dA was 9, or was 5. And df dx is just df dA times dA dx. So that's also 5. So there's a very simple mechanical pattern that starts popping up if you want to compute the derivative of the total output expression as a function of any of the inputs. So you compute the derivative of f with respect to an output. You just propagate it back. And then here you have the derivative of a with respect to its inputs. You keep moving backwards using chaining. So in some ways I can do this completely pictorially. Like if I have a plus, so if the change in the overall function with respect to this node is 10, well, this node's derivative with respect to x is 1.